Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome JOOST, right? I will not dare to pronounce the surname. But he came here all the way from the capital of Europe, from Brussels, and he will tell us everything and more about generalizations of Yetter-Drinfel'D modules and the center construction of monoidal categories. You know, for me, anti-Yetter-Drinfel'D modules are much closer to my heart, but they appeared in abstracts. I hope they have their portion about. It's all yours. Take it away.
Thank you, Piotr. There will be anti-Yetter-Drinfel'D. In fact, maybe I should start by saying that many of this is the fault of Piotr, because, well, first of all, the reason that I'm here is because Piotr invited me. Thank you very much for this. Last time we spoke, it was in Brussels. Then you at Brussels for a conference, and then you invited me to come here, and I noticed that half of the speakers of our event in Brussels also appear in the line with you. So at least our meeting was good for something. So another reason why it's all the fault of Piotr is that it's a joint work with Ryan Aziz, and I started to talk with Ryan about Yetter-Drinfel'D modules and Generalizations modules after Ryan talked with you. At some point, he applied for a postdoc grant or so, and then he came back and we started discussing about Yetter-Drinfel'D module. I think something completely different than what you were discussing with me, but we ended up writing this. It's still in progress. I hope to have the preprints ready by now, but it should come out at some point at least. And another thing, yes, indeed, why it's Piotr's fault is because these Yetter-Drinfel'D modules, maybe you don't remember it, about 20 years ago, you were in Brussels for a talk exactly about anti-Yetter-Drinfel'D modules. You get that? And it was a talk, I was in the middle of my PhD, and I still remember that talk very well because it was the first time that I could understand the talk, more or less. You never understand the talk completely, but I could understand most of it from the beginning to the end. And I was so happy at the end of that talk. And I looked to my neighbor who just started his PhD, and I said, this was a very nice talk, very clear. And he said, I didn't understand a word of it. But he had just started a PhD a few months ago, and I was already there for a few years. So. But anyway, it is since then that Piotr spoke about these Yetter-Drinfel'D modules that they stayed somewhere in the back of my mind, because one of the things you said there is that when you take a tensor product of a Yetter-Drinfel'D and an anti-Yetter-Drinfel'D, it is again an anti-Yetter-Drinfel'D. And I remember that at that point I was thinking, and what happens if you tensor two anti-Yetter-Drinfel'D modules? Does it become a usual Yetter-Drinfel'D, which is not the case, but this is one of the things that I will explain more.
Okay, since we are telling stories, let me add, thank you so much. I'm really happy to be culpable for so many guilts. I feel really guilty now. When I was giving a talk in Kansas about Yetter-Drinfel'D modules, Professor Yetter was in the audience, and I had to apologize, but anti-Yetter just means that I have anything against him personally. Just twisting the ambiguity. Anyway,
okay, so before going to the generalized Yetter-Drinfel'D modules and so on, I will start with the well-known things, so the usual Yetter-Drinfel'D modules and how they appear. So throughout here, H is a bialgebra. At some point, there will be Hopf algebras, and I work over a commutative ring. Maybe at some point you need some flatness conditions, or you can just work over a field, and you don't need all these, of course. But basically, H is a bialgebra, K is just a commutative ring. Okay, then you have these three categories. One is the Yetter-Drinfel'D modules. There is the center of a monoidal category of H modules, and modules over the Drinfel'D double. And these three are interrelated, so you have under good conditions equivalences between all these categories. And this is of course very well known. I will review it because we want to generalize it then to another setting. So
I didn't mention it here, but to have a Drinfel'D double, usual algebraic set, it takes to be finite dimension.
Yes. So there is, I mean, you always have functors like it, but indeed, yeah. For this one, you need finite dimensional, unless you go a bit further, not just with Hopf algebras, but with...
Yeah, so I know that Voronovich analyzed this construction in his functional analytic settings.
Okay, so let's start with the Yetter-Drinfel'D modules. What are these? I consider left-right Yetter-Drinfel'D modules. A left-right means that on the left we have an action of the bialgebra on a module, and at the right we have a co-action. So we have the same vector space, both with an the same K module M with an action of H on the left and a co-action of H on the right. And then there is some compatibility condition. And so here, maybe this is not a compatibility condition that you are used to, because I have the co-action on an action, and there is this additional H1 here. But if you, I told in the beginning, I work with a bialgebra, you can do this for a Hopf algebra. And if you have a Hopf algebra, and even Hopf algebra with invertible antipode, or maybe just a bialgebra with an op antipode, then you can move this H1 to the right. And so you have this maybe more common expression with the inverse of the antipodes appearing. So that's the compatibility you have between the action and the co-action in order to have left-right Yetter-Drinfel'D module.
So what is op antipode?
Op antipode is like the inverse of the antipode. It means it satisfies a twisted antipode condition. So usually for an antipode, you have S of H1, H2 is epsilon of H1. And then for an op antipode, you have the twisted version of it. So H2, H1 is epsilon of H1. Yeah, and of course,
So since you are not using antipode at all,
no,
it means that you allow
the Hopf algebra here,
bialgebras admitting an op antipode without antipode.
yeah, that can happen. Yeah. So
Okay.
it's fine. At some point, you need both the antipode and the op antipode. But here for this formula, you just need the op antipode. Okay. Good. And then so these Yetter-Drinfel'D modules are related to the monoidal center of the category of H modules. So what does it mean? We have a bialgebra, so that means that the category of modules is monoidal, which tensor products the K tensor product, when you act on a tensor product by first doing the co-multiplication and then acting on both legs. Right? So this is usual way to make left modules here over a bialgebra into a monoidal category. And as for any monoidal category, you can consider the center of this monoidal category. This is a graded monoidal category that you construct out of your category. How do you do it? You objects in your new category, the center of your monoidal category, are pairs consisting of an object together with what we call a half braid. And this half braid is a natural transformation from tensoring with the object on one side to tensoring with the object on the other side. These have to satisfy some compatibility conditions. The first one is usually a hexagon condition, but I didn't write the associativity constraints, so it's only a triangle. And then there is a compatibility with the monoid. What is the relation between the center and the Yetter-Drinfel'D modules? Well, here we have a natural transformation between two functors on a category of modules, and a natural transformation between two functors on module categories. They are determined by taking that natural transformation just in the ring over which, of the algebra over which you work. So it's enough to know beta H for H, the Hopf algebra, to know beta everywhere. The reason is the diagram here at the bottom of this page, where you can go from H to any H module X just by left multiplication, right? And naturality then tells you that you can really determine beta on any X if you know beta H. So it's enough to know beta H, and in fact, not just beta of H, but it's enough to know to evaluate it on H in the unit, right? So it's enough to know beta H on one tensor M, and that gives you exactly then a co-action or a candidate co-action on the left module M. So what does it mean if I take, this is the one I have to use, if I have this object in the center, it consists of a left module, and the additional structure, this half braid, translates into this morphism rho M, which is basically a candidate co-action. It goes from M to M tensor H. And then if you check what this has to satisfy, well, we want beta to be left H linear. And when you check what means left H linearity, that's exactly the Yetter-Drinfel'D condition. If you check what it means for beta to satisfy the half-braid conditions, you have that triangle, the two triangles. Well, it means exactly that the coaction is a true coaction. The candidate coaction is co-associative and co-unital. And then finally, if you want beta to be an isomorphism, so this half-braid to be a true braid and not just a pre-braiding or a lex braiding, but beta to be invertible, then you need the bialgebra to be hop. So here you really need a true antipode, not an up antipode, the true antipode if you want these betas to be isomorphisms. But this way you see that you can go from Yetter-Drinfel'D modules to the center. And then, so yes, this is what we have here. So an object is in the, I have a module with a left action together with this half braid in the center, if and only if the coaction associated to the half braid turns it into a Yetter-Drinfel'D. So these categories are in fact isomorphic. And then the third version is indeed where H is finally generated and projective. Then you can construct this Drinfel'D double out of H and the dual of H with a somewhat involved co-multiplication. But it turns out that the Yetter-Drinfel'D modules are then also isomorphic to modules over this Drinfel'D double. Okay. So yes, and this Drinfel'D double then becomes a quasi-triangular Hopf algebra because its category of modules is braided. And yeah, this is what I also want to say. So if H is not finally generated and projective, then you don't necessarily have the Drinfel'D double as a Hopf algebra, but you still have some coring over H, whose co-modules are exactly the Yetter-Drinfel'D modules. Good. And these are the classical Yetter-Drinfel'D modules, but there are generalizations of these. And that's what we want to look into. And the first generalization are the anti-Yetter-Drinfel'D modules. So what is the idea here? Well, we just interchange the roles of S and S inverse in the usual Yetter-Drinfel'D compatibility condition. And when you do this, you get yet anti-Yetter-Drinfel'D module left-right, so have the left action, the right coaction, and the compatibility now. Remember, before we had an S, an op antipode here. Now it's the usual antipode that appears there. You can do the same trick as before and move it completely to the left, and then you get a square of the antipodes appearing. Okay. So these are the anti-Yetter-Drinfel'D modules, and what is known about them? Well, there is some anti-double for them. The anti-Yetter-Drinfel'D modules, you can tensor them with Yetter-Drinfel'D modules. So they become some kind of a, what I call an category. So other people like to call this a module category over a monoidal category. So there is a tensor product between anti-Yetter-Drinfel'D and Yetter-Drinfel'D modules landing in anti-Yetter-Drinfel'D modules. And there is also a more recent generalization of these anti-Yetter-Drinfel'D modules with higher powers or other powers of S. So you have S squared here, you can put S, any even power of S at the left, or an odd power of S at the right, and then you have these higher Yetter-Drinfel'D modules. And so if you tensor two anti-Yetter-Drinfel'D modules, you get another higher Yetter-Drinfel'D module, but with a S to the power 4. So
yeah, to go back to Yetter-Drinfel'D, you need to tensor anti-Drinfel'D with anti-Drinfel'D contra module.
Yes.
Then go ET travel to a Yetter-Drinfel'D module. If you don't mind, let me weigh in concerning this anti-double, because I think it's interesting. It's a Galois object. Yeah, this is a Galois object over the Drinfel'D double, and there was a serious problem of whether or not, if you have a finite dimensional of algebra, does it always admit a modular paired involution, which is a one-dimensional Drinfel'D module? Because if it does, then in fact this Galois object is isomorphic to the scope algebra. But the PhD student of Uli Kramer did his PhD finding a counterexample.
okay.
This was very difficult. He constructed an example of finite dimensional of algebra, which does not admit modular paired involution. So there is no one-dimensional anti-Drinfel'D module. So it means that this Galois object is really a Galois object in the function.
Galois objects will appear also. Okay, so now a bit more general, instead of just working with the antipodes, Panaiti and Stage introduced these generalized Yetter-Drinfel'D modules of the following kind. You have two Hopf algebra automorphisms, alpha and beta, on your Hopf algebra H. And now generalized Yetter-Drinfel'D modules in their sense, so depending on the alpha and the beta, is again a left module, right co-module, where now in the compatibility condition, you see the alpha appearing at the left, the beta at the right, or if you want to put everything at the same side, you have beta here and here alpha composed with the op antipode. So you have these kind of generalized Yetter-Drinfel'D modules for every pair of alpha and beta. So in particular, if you take, for example, beta to be, what is it, S squared and alpha the identity, or no, beta the identity and alpha S squared, you have the anti-Yetter-Drinfel'D modules as before. And what they showed, and I will come back to this at the very end of this talk, is that the kind of disjoint union of all these categories of anti-Yetter-Drinfel'D modules, they form a monoidal category or group crossed braided monoidal category in the sense of derived. So there is a nice structure for these. And what now I would like to study is look into are these more generalized Yetter-Drinfel'D modules that were introduced even before by Kanepeel, Militaru, and Zoog in their book. There appear these generalized Yetter-Drinfel'D modules. How do they work? Well, you consider now two bialgebras, H and K. And over these two bialgebras, you have a bi-co-module algebra. So an algebra A together with the co-action of H on the left and of K on the right. And you have a bi-module co-algebra C. So you have a co-algebra with an action of K and H, but reversed. Okay. Then the generalized Yetter-Drinfel'D modules over this datum of H, K, A, and C is a module that is at the same time a left A module, a right C module, a right C co-module, a left A module, and then the compatibility condition reads like this. So again, you have a compatibility between action and co-action. But you see the antipode is no longer, the antipode will appear if I have the equivalent thing. So again, as before, I can move this A-1 to the right using the op antipode, okay. But what I wanted to say, yeah, you can check that everything fits well. So M has a left A action, and the co-action of M lives in the co-algebra, which has a left K action, right? And indeed, the where is it? It's over here. I have to look. So M1 lives in C. And you can act on elements in C on the left with K, which fits because A has a right K co-action. Okay, so you have to look a little bit that everything works, but this is a formula that perfectly makes sense. And it's a kind of generalization of Yetter-Drinfel'D modules in the spirit of these Doi-Hopf modules and Doi-Copeland modules. Okay. So,
sorry, what is this S bar? Can you remind me?
S bar is the inverse of the antipode, basically, the op antipode. As bar. So that's what allows you to move this A-1 to the right using a convolution.
But why not just write S inverse?
Because in principle, I don't need S to be bijective if I have just an inverse of the antipode, let's say, without having an antipode. You can have a bialgebra
I've got you.
with an op antipode without having an
Sorry, you answered this question before.
Sorry. Okay, so yes, again, when the co-algebra is finally generated and projective, you can construct some kind of a Drinfel'D double. So out of the tensor product of C dual with A, you hook up a suitable algebra such that the modules over this algebra are exactly these generalized Yetter-Drinfel'D modules. And if it's not finally generated and projective, these generalized Yetter-Drinfel'D modules are still co-modules over a suitable core. Okay.
I have a question about this double. What kind of a structure it is with respect to H and K?
Yeah, that's what I exactly want to answer in my talk, because they just constructed the objects and saw that the modules over it were these Yetter-Drinfel'D modules. But I want to understand how it is the monoidal structure and what is then the structure of this algebra, basically. So I will answer this during the talk. Maybe not as explicit as you asked, but then we can come back to it later. Okay, so usual Yetter-Drinfel'D modules pop out as a special instance of the generalized ones, where you take H, K, A, and C all just to be H, then you have the usual Yetter-Drinfel'D modules. You also have alpha beta Yetter-Drinfel'D modules. What do you do there? Well, you have H and K are still H, but you change either the A or the C. So instead of just taking H for A, for example, you can take H as an algebra, but you deform the coactions using your Hopf algebra morphisms, alpha and beta. So alpha and beta here, remember these were Hopf algebra automorphisms of H. If you define a coaction, which is a usual co-multiplication, but on one of the two legs you use the alpha, you have a kind of new coaction, which is isomorphic to the original one. It gives you another bi-co-module algebra, and using these kind of twists on the coactions, you get that the generalized Yetter-Drinfel'D modules with an alpha and a beta are the generalized ones of Militaru, Canapeel, and Zhu, using as algebra this H with the deformed coactions. Or you can also deform the actions on the co-algebra just in a similar way. Right. So in particular, the anti-Yetter-Drinfel'D modules and the higher anti-Yetter-Drinfel'D modules arise in this way. Okay, so what are now the questions that I want to answer is, well, these generalized anti-Yetter-Drinfel'D modules, do they arise by some center construction on some monoidal structure? And moreover, what is then the graded monoidal structure of these Yetter-Drinfel'D modules? And by answering this question, I more or less answer your question as well, because if I know what is this monoidal structure and how does it relate to the monoidal structure of usual Yetter-Drinfel'D modules, I also know how the double relates to the double over the usual H and K. Okay. So that is what I want to do. And in order to understand what is going on, let's take a step back and look what we, in fact, we are doing when we are studying Yetter-Drinfel'D modules. So there is this Tanaka duality that gives you this correspondence between algebraic structures and structures on the category. So H is a bialgebra. This is in correspondence with monoidal structures on your category of modules. So for an algebra, I should say this for an algebra H, there is a bijective correspondence between monoidal structures on the category of modules using the K-tensor product and bialgebra structures on H. And what we do when we go to Yetter-Drinfel'D modules is that we lift this monoidal structure to a braided monoidal category. And so there is a monoidal functor from Yetter-Drinfel'D modules to this monoidal structure on the H modules. Now, for generalized Yetter-Drinfel'D modules, we do not work with modules over a bialgebra, but we have modules over a bi-co-module algebra. So what does it mean? Well, when I have an A to be an HK bi-co-module algebra, it means that the category of modules over A is not a monoidal category, but it becomes a bi-actigory over the monoidal categories of H modules and K modules. And again, bi-actigory, I mean there is an action of the monoidal category of H modules on the category of A modules on the left, and an action of the monoidal category of K modules on the category of A modules on the right.
They are monoidal due to different reasons. Monoidal over K is because K is commutative, and monoidal over H because H, no?
No, H is H and K are two bialgebras, right?
Okay. Sorry. Okay.
I have two bialgebras.
Yeah.
So I have two monoidal categories.
Of course. Sorry.
So my base ring is a little k. So there is.
That's what that confused.
Yeah. Small k is the base field or base ring, and big K is just a
monoidal biametrical problem.
Yeah. So both are monoidal categories, and both monoidal categories act on the category of A modules if and only if A is a bi-co-module algebra. Okay. So indeed, you act on a tensor product by just co-multiplying the A. On the left, you get something in H. On the right, you get something in K, and then everything fits well. Okay. Now, what we want to do is when we go, oh, this is a further remark. So if I have different bicomodule algebras, then I can combine them into new bicomodule algebras. So if you have now I have 4 Hopf algebras or 4 bialgebras, H, K, and another L. I have A to be a bicomodule algebra over H and K, and B, which is a bicomodule algebra over K and L. So I have the same K appearing for A on the right and for B on the left. Then we can take the cotensor product of A and B over K. This will again be a bicomodule algebra, at least if you have some flatness for that the cotensor product does not cause any problems. And you can tensor A modules and B modules into modules over this new bicomodule algebra A cotensor B. So when you then put all of these together, what you get is in fact a B category. So you have these monoidal categories of modules over bialgebras. They are monoidal categories. And in between these monoidal categories, you have these bicategories. If you put all of these together, you get a bicategory. A bicategory meaning you have 0 cells. My 0 cells are the Hopf algebras. We can suppose them to be flat so that this cotensor product does not cause any problems. So we have Hopf algebras. Then 1 cells are modules over some bicomodule algebra. So they are like graded over the bicomodule algebras. You can put all of them together. So in between 2 Hopf algebras, the Hom category between an H and a K is the disjoint union of all the module categories over all bicomodule algebras. Okay, so this is a monoidal structure that there is on modules over bicomodule algebras. It's no longer a monoidal structure, it's a bicategorical structure. And now what we want to do is we want to lift this to Yetter-Drinfel'D modules.
Sorry, is there some, if you have this disjoint union,
Yes.
does it create some set of theoretical problems here?
Well, this disjoint union, it's in fact on my next slide. It can be a bit annoying. Like if you want your categories to be abelian, then this disjoint union is annoying because how you make, for example, a coproduct, a direct sum of a module over an A and a module over a B, when A and B are different, their coproduct is no longer a module over A or a module over B, but you have to make something bigger. So in fact, if you want to work in an abelian setting, you do not consider disjoint union, but more something like a coproduct where you have to take basically families of objects. So you think about this coproduct, you think about taking direct sums of this kind of modules, right? And then things work better than when you work just with disjoint union.
Yes.
Well, depending what you want to do.
I would prefer to do this.
Yes, I agree. Okay, the point that in the literature you find often these disjoint unions. This is why I want. And so what we want to do is to lift this structure to the generalized Yetter-Drinfel'D modules. Okay, so the first thing you find then, if you try to do this, is the following. Indeed, you have some big category structure on the Yetter-Drinfel'D, the generalized Yetter-Drinfel'D modules, or if you just take it in the parts. If I have 2 categories of generalized Yetter-Drinfel'D modules, so again, I have 4 bialgebras, H and K, and over these H and K, I have a bicomodule algebra and a bimodule coalgebra, and I have these generalized Yetter-Drinfel'D modules here. Then I have the same K, right? But I have a second different bialgebra. I have a bicomodule algebra over it, a bimodule coalgebra over it, and I have these monoidal category, this category of generalized Yetter-Drinfel'D modules. And now I can tensor these together. So 2 generalized Yetter-Drinfel'D modules, if the same bialgebra appears once on the left and once on the right, you can make a new category of generalized Yetter-Drinfel'D modules where you keep the first Hopf algebra here at the left, you keep the right Hopf algebra at the right, and the two bi-comodule algebras, you co-tensor them together into a new one. The two bi-module co-algebras, you tensor them together into a new one. And then the structure you need, or the way you have a new action of the co-tensor product or an action over the tensor product is in the most naive way that you can write down the formula, but everything works well.
Aha, now why is this last tensor product over capital K?
Because I want this
Balance.
C.
Because it's really balanced, okay.
Yeah.
Okay.
It's a balance.
So
So it's exactly the dual thing of what happens here when you take the co-tensor product over.
The last thing would be even nice in parentheses, right?
Yes, indeed.
Okay,
That would be indeed better to have these. Yeah, this here. Yeah.
so everything is almost perfectly dual with respect to
Yeah.
this lower and
Yes.
indices, except that you need some flatness condition for
For the tensor product, co-tensor
Tensor product.
behave well. Yeah,
Right.
indeed. But that's the only reason why I need this flatness is for this co-tensor product to be associative.
Just flatness, no co-flatness.
No, that's because tensor products are always associative. Okay, so in the same way as for the modules over bi-comodule algebras, you can put all these things together now in a big bi category. So zero cells are again the Hopf algebras or flat Hopf algebras. The one cells are generalized Yetter-Drinfel'D modules of all possible kinds that exist. And so you can take this disjoint union or dot product, if you prefer, of all these categories. And then you have some kind of a B-graded B category, graded over these algebras and co-algebras. Okay, good. Yeah, this is like the remark that you can go to the co-tensor product instead of disjoint union. And what do we find in particular? That is something you will recognize from the anti-Yetter-Drinfel'D things. So in particular, we find that if we would take at the left here, A and C and H and K all would be the same. So you have H, 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 H at the left. Then this K would also be an H. So this is not changing. And then the co-tensor product here would be the co-tensor product of H over H with B. You don't change it. Here, the tensor product over H with H. So then you just have an action of a monoidal category. So indeed, we find that these generalized Yetter-Drinfel'D modules are again bi-categories over the Yetter-Drinfel'D modules over the two Hopf algebras. But there is more, right? So not just these actions, but you have this way of composing them. And when you go back to the higher anti-Yetter-Drinfel'D modules or it's the same thing that happens, right? So these co-tensor products make that if you have two anti-Yetter-Drinfel'D modules and you take that co-tensor product of these deformed algebras, you have one times the antipode that shows up another time and together you get a square.
These are like left loops and right loops.
What do you mean?
Because these act like rings.
In the big category settings, so
Yeah,
these are indeed the loops. Yeah, they go from one point to another.
By the way, is it obvious that under this assumption of flatness, these categories are Grothendieck categories?
Yes, because they are co-modules over a flat co-ring then. So the flatness of the Hopf, but you need that the C's will be flat in that case. Yeah. When the C's are flat, everything is Grothendieck.
Sorry, two things. One is that you realize I have 90 minutes, right? Not 60.
Yes. I have no idea how fast or slow I am.
Because you used up 1/3 of your time and almost half of your slides. So
Okay, well,
no need to slow down. And secondly, I would like to somehow, I love this picture of having categories, but I somehow cannot distinguish which is which when I look at what is written here. So which part I should look at as Yetter-Drinfel'D and which one as anti-Yetter-Drinfel'D?
yes.
Please say it again.
I will do this. Okay. So if I take a general instance of this, where I take all of them to be H.
Yep.
Oops.
Yes, do.
No, one more. Yeah. So H. Then these are the usual Yetter-Drinfel'D modules. Okay. Then what I can do here, if I want anti-Yetter-Drinfel'D modules, is take again H and H. And I put an H here and the co-algebra, let's say that I deform the actions with identity and S squared. Then these are anti-Yetter-Drinfel'D modules. And what you end up with, so if you go here, you will go to YD. In between brackets, I had all H's, so this stays. Did I do something wrong?
So it's like passing from S to S bar. On the right hand side, the second factor.
Yes.
You have this identity on the left hand side and you have this S squared on the right.
Right.
Yeah. So is it equivalent to replacing S by S bar?
Yes, yes,
Okay.
yes. This is in fact what came since I can, oops. No, I'm going to the wrong side. It left is different from this. So where is it? I'll get back. It was here, right? So no. Where were these alpha, beta, Yetter-Drinfel'D modules?
Yeah, yes.
So
I remember
this
yes.
S bar that appears in the other formula. So if you take alpha to be the identity and beta the identity, you have a formula with S bar. If you take alpha to be S squared, then this S bar becomes an S. That's how you get anti-Yetter-Drinfel'D by taking alpha being S squared.
Mhm.
Okay.
Yeah.
45. Yeah, here I was. Okay. So, and here I was right. Yeah, and here you also, let's see if I can again write. If I would take two,
It should be able.
to write, but is it? Yeah, it's this one.
Yes,
It isn't
that's strange.
right anymore. Yeah.
Right, let's try again. How about it?
I
See, sometimes it just.
Okay. So if I put this S squared here and there, and then I tensor them, that's how you get the S to the power 4, right? Because it's just tensor product over H, so it's just H tensored with itself. It's only the action where the powers of S are adding up, or the alphas and the betas will be composed in the.
That's a very nice picture, yes. But see, I couldn't see it when you just speaking it. I needed to have it written down.
Okay.
So this covers all these cases that this Yetter-Drinfel'D are. It's a left category, it's a right category.
Yes.
Yeah.
And when you put them together, you get higher.
Yes. Yeah. Nice.
Will you at any moment go into contra modules?
No. I know Ryan at some point told me there is this link with anti-Yetter-Drinfel'D and contra, but it's something, we didn't look into yet. But it's something I'm curious about because I found it very strange that these are contra modules that show up. So
it's very mysterious, and this is chapeau bas for Tomasz Brzezinski, who unraveled the whole theory of anti-Yetter-Drinfel'D contra modules. Because one of our immediate observations was that if I want to somehow go back, if I want to untwist my anti-Yetter-Drinfel'D module to become again a Yetter-Drinfel'D module, it's not by anti-Yetter-Drinfel'D module, but we didn't know what it was, and it turns out to be a contra module. But
I would, the way I would do it is just by putting an S-2 here, right? So that's will do it as well because I have S-2 and an S power 2.
Yeah, you're probably right. Yes, of course. You can think,
probably
higher powers.
Yeah, S-1 somehow creates a contra module. I know.
No. But maybe they are equivalent if you categorize everything further.
Yeah.
Because what are contra modules? They are, in a sense, modules, but not for the dual algebra to some coalgebra, but with respect to some monads.
Yeah.
Okay? In the language of monads, all these differences disappear.
Yeah. Again, yeah, but yeah, this is still something on our to-do list to look into it, or yeah, there should be a relation, but I don't know how. Here, I would, like I said, I would use s to the power -2, and it should also work to make it turn it into usual method.
Because we went slightly further with Gavin Byrne, but we never wrote it down. I mean, we wrote it down in scribbles, but not even in preprint. That you can combine these contra modules and modules and have something more general. And then they are modules over some very funny animal, which is in the spirit of Yetter-Drinfel'D double, but it's much more general. And you can do things without analysis. But it's just pure algebra. But you can look at modules over these very general anti-Yetter-Drinfel'D doubles that combine together anti-Drinfel'D modules and anti-Drinfel'D contra. So we somehow, in a very naive, simple way, combined it together. But I am pretty sure that Tomek is right. If you look at it abstractly,
Yeah,
from categorical point of view,
at some point everything collapses.
I wouldn't say collapses. You see where things come from.
Yeah.
Because at this stage it's by some simple try and error, and some things match, some things don't match, and you don't understand why. So, yeah, okay. Anyway, there's a side question about contra.
Yeah, so we have this.
May I comment? Yeah, because if you're asking about this anti-Yetter-Drinfel'D modules, contra modules, yeah, but almost forgot. But I have a paper with Serkan Suto about Takeuchi-Galois duality. And then we did something very similar. We are not interested in all possible Yetter-Drinfel'D modules, but we are interested in anti-Yetter-Drinfel'D modules. And we did something very similar to this. So if you are interested.
Yeah, sure. I'm sure that our references is still not complete, so I would be happy.
It's only one page.
Yeah.
Some remarks, but the construction is very similar. But of course, yours is very general, very nice.
Thank you. So, but this is not, it's only the bi-category structure. I mean, I went some center type thing and I went braidings. And that we don't have yet here. That's what we want to do. I want to see if the generalized Yetter-Drinfel'D modules can appear as some center, but in view of what we saw before, it should not be just the center of a monoidal category, it should be the center of these B categories and center of a B category. So first I thought, what could be the center of a B category? And then I thought about maybe something, you know, this periodic table of monoidal categories or higher categories. You have on the 0 level sets, then you have a monoidal structure on it. On a set is just a monoid. And if you have two compatible monoidal structures on a set, you have a commutative monoids. And then there it stops. On categories, you have categories, monoidal categories. And then instead of commutative, you have braided and symmetric. On a 2-categorical level, you have 2 categories or B categories, monoidal 2 categories, braided monoidal, syleptic, symmetric. So there are always more objects that appear. And then there are relations between these things. So a monoidal category, you can view it as a 2-category with only one object. If you have a 2-category with one single object, it's a monoidal category. And a braided monoidal category, you can see it as a monoidal 2-category with just one cell. Again, with one object. That's a braided monoidal category. So first, when I thought if we want to go from monoidal to braided monoidal category, on the 2-categorical level, I should go from a 2-category to a monoidal 2-category. So that's the same kind of way you move here horizontally, but that is not working well because the kind of braided monoidal category that I want to build out of these Yetter-Drinfel'D modules. So the objects in my category were H, right? So if I just have H, and I look to the loops from H to H, as you said, you have the usual Yetter-Drinfel'D modules, and I have a braided monoidal category around every zero cell of my B category. So what I want to build is some kind of 2 category or B category, where around every object, I have a braided monoidal category. And if I take a monoidal 2 category, I only have a braided monoidal category around the monoidal unit of this 2 category. So it's not this that I need to do. So
sorry, when speaking about monoidal 2 category,
yes,
on which level it is monoidal?
it means that on all levels. So you have 0 cells, 1 cells, 2 cells, and you can tensor the 0 cells, the 1 cells, and the 2 cells.
Okay.
So it's an additional, it's in fact, you can go on here, you have 3 categories. A monoidal 2 category is a 3 category, 3 category with 1 object, that's a monoidal 2 category.
So I have a stupid question. What does it mean, syllactic?
Syllactic is something that is in between braided and symmetric, but that can only be understood at a 2 categorical level. So it's the higher you go, the more horrible it becomes. You have always an extra type that shows up. It's the same that if you are just working with monoids, you have nothing between braided and symmetric. You just have commutative monoids. But on 2 categories, you have something between braided and symmetric, some new type, syllactic, that appears.
But does it mean anything in English?
Yeah, I don't know what the word.
Probably in Greek.
I have
Means something.
no idea what is the meaning of syllactic, but
Or
Syllactic branching, syllactic. Synapsis. The meaning of synapsis is the use of a word to modify or govern syntactically 2 or more words. With one only, this is very complicated. The use of a word to modify or govern syntactically 2 or more words, with only one of which it formally agrees in gender, number, or case. Does it agree with it?
anyway, I gave the slides because to say that this is not the direction I wanted to. So it was maybe of a detour. Is that no? Okay. So what I want to understand is what it could be kind of center for a B category, right? So I have 2 monoidal categories that act on the same category M. So I can tensor elements of C with elements of M into elements of M, and I also have an action of the second monoidal category D on the right. So I have this B category, and I want to have some kind of a center for this B category. Then what you need for this is an opmonoidal functor from one to the other. Okay, so you have these 2 monoidal categories, and I have a functor in between them, a functor that satisfies together with a natural transformation like this. So if I apply my functor on a tensor product, I can go to the tensor product of the 2 images. Right? This is what I mean by opmonoid. And having this, we can create a lax or weak, whatever you want to call it, center of my B category with respect to these 2 actions and the opmonoidal functor E between them. So basically what we want is, so you have an object in M, you have an object in C, and you can tensor them together. So I can act with the category C on the category M, so I can take an object in the monoidal category C and tensor it with an object in the category M. And I want to move the C to the right. When I want to move the C to the right, in order to tensor it from the right, I need it to be in the category D. So that's why I need this functor to go from C to D. When I have this functor from C to D, I can say what is a braiding in such a B category. So I can act on the left on the left with C. I turn the C into something in D so that I can act with it on the right, and I want my braidings to be like this.
does anything special happen when this psi is a strong
Yes.
monoidal?
Yes, yes. So I believe so. Here it's just monoidal, but it will become strong for a reason in a minute.
On the next slide.
Yeah. Okay. Or maybe in two. Okay, so the next slide is the compatibility condition you need on this C. So the usual compatibility you have on a braiding, on a half braid is a hexagon condition. Here we have one additional arrow, which is coming from the monoidal structure. So instead of a hexagon, you have a heptagon condition now with this monoidal structure appearing as additional information. But for the rest, it's very similar to usual centers and braidings. And then what you find is that this relative center, so objects with this kind of half braid, they becomes a B category over the centers of the two monoidal categories. So you have a B category over two monoidal categories. You can go to the center of the two monoidal categories and the E relative center of the B category. And then it's again a B category. Yes, here is how you build this action. You, on the object part, it's coming from below, and then you have to say how the half braids are combined, and that you do in the usual way. The half braid on a tensor product is made up of the half braids of the two parts, right? And so you can, no, it's written here. So the half braid on the tensor product is made up by combining the half braids on the two parts tensored with identities. So it's again, it's not too hard to come up with this. If you see what you need, it's the first guess that works. Okay. Yes. Now we can say what is then braided or a pre-braided B category. So if I have a B category over braided or pre-braided categories, what would be then a braided B category? It's again a B category where you have betas of the same kind, right? Now not half braids, but true braids, right? Our aim is that this center will be a braided monoidal category in such a sense, right?
Could you remind us what is pre-braided?
Pre-braided is braided, but without the braidings being invertible.
Ah,
braided is where these are inverted, they are just arrows. This is related to your question why I needed just an up monoidal and not a strong monoidal functor. Because here for the moment, just arrows and not isomorphisms. Okay. These betas then, in order to have a braiding, you can write down
pre means glass.
Yes, yeah. You have again hexagons that become heptagons with a size the opmonoidal structure that appears over here, and there are 3 of these conditions. Okay, but that's not the most important part. What we get is the following. Okay, so if we have this, there is a little mistake here. I see this should be my category M, not C. This is F. Okay, so I have the C and the D, which are monoidal categories, and I have M, which has a B category over them. Then I have this functor E going from C to D, and I can make this E relative center of M. This E relative center will then become braided with respect to that E, using as braidings exactly the half braids, basically. So you get that when you have a B category and this opmonoidal functor E, you get that the relative center becomes braided with respect to E, but in order to be braided, we need one additional condition, namely that the functor E can be lifted to the centers. And here is the answer to your question, what happens if E is strong monoidal? If E is strong monoidal, then you can always do this lift, because if it is strong monoidal, then you also find a functor between the centers. So the strong monoidality or will allow you to do this. Okay, but that's
so in a sense you are mimicking this property.
Yes, yeah.
Of the existence of this lifting.
Yes,
you are assuming it.
Yes, yeah. I will make it. No, before I do that, let me say this. So a few remarks. center and braided version of B categories. If you take the two monoidal categories to be the same, and E to be the identity, and M to be also this, then you have the usual center of monoidal category, or center of a B category of the same C. Yeah, I mean, it corresponds with structures that were known. And another relation maybe worth to mention is some very recent work of Lagwitz, Walton, and Yakimov, who have some kind of reflexive center. In their setting, they have a braided monoidal category. And when you have a category over a braided monoidal category on one side, it also becomes an category on the other side. Thanks to the braiding, just like when you have a commutative monoid, you have an action of a commutative monoid from the left, it's also an action from the right because your monoid is commutative. So if you have a braided monoidal category together with an action on another category, you can also turn it to the right and you can consider the center with respect to this. And that's a special case of our construction.
So the coactions are turned into co-opposites in this third point.
Now here it's with respect to the co-opposite tensor, the opposite tensor product. So this co here means that you reverse the tensor product. Yes. So I mean, C is braided, okay, right? And then the braiding gives you an up monoidal functor from C to itself. So let me, what's this? So when C is braided, I can consider the identity functor from C to C, yeah, as a monoidal functor, but I can, in order to have a monoidal structure on the identity functor, I need to say what happens if I tensor before I do my functor or after I do my functor. So what I do is I take this monoidal category with my tensor product, but on the right, I take the opposite tensor product. Right?
Yeah, so I'm wondering why pole, but not op.
You can call it op.
Okay.
Because op I used to change the direction of the arrows.
Okay.
Co is like the
tensor product.
arrows, but a tensor product.
Okay.
Yeah.
Okay. Thanks.
And so the braiding is a monoidal structure on the identity functor going from C to C with the opposite tensor product. Yeah. Okay. Good. But this was the general setting. I want to go back to the Yetter-Drinfel'D modules. So what do we want to understand? To recall is that when I have generalized Yetter-Drinfel'D modules, in the sense that I have two Hopf algebras and a bi-comodule algebra over it and a bi-module co-algebra, this thing I want to see as some generalized center. What did we know? Well, we knew that if we have just A to be a bi-comodule algebra, then modules over A become a B category over the two monoidal categories of H modules and K modules. Okay? Now I want to make a center of this bi category in the sense of what I explained before.
Yeah, but please explain to me what is happening with objects of this AM or MA. Okay.
These are,
yes. So these are simply modules.
These are modules over A. Yeah. So this was
so object. So except A is HK by comodule algebra.
Yes.
About modules over this algebra, you assume nothing.
No. So I mean, I have modules over A, and I can tensor these with modules over H on the left, right? Using the coaction of H on A, I can tensor these together into new, again, modules over A, right?
So there is no any compatibility condition between this module structure and these actions of H, K.
Well, the compatibility is that I have a bi-comodule algebra, right? So doing but
the module is not acted or coacted by H or K.
No.
Okay.
It's what you have is that the whole category of H modules acts on the whole category of A modules. just thanks to the fact that you have a bi-comodular algebra.
Yes.
Okay. What I want to do now is to have a center of this bi-actigory. And so remember in the general setting, when I needed a center of a bi-actigory, I needed an op-monoidal functor between the two monoidal categories. So what I want to understand now is what are op-monoidal functors between two categories of modules over bi-algebras or Hopf algebras. And for that, we have some things that are in fact well known. So if I have a functor between two module categories and I want it to be co-continuous, so preserve co-products and quotients or to have a right adjoint, it just comes from tensoring with a module, or tensoring with a binding.
It will become monoidal.
Yes, this is just perfect. Use 2/3 of your slides and 2/3 of your time.
Okay. So op-monoidal structures on such a functor are then exactly co-algebra structures on C. Co-algebra structure, making it into a bi-module co-algebra.
Yes.
Bi-module co-algebra. Then remember what I needed in order to have that braiding, and that's the braiding on the B-actigory, was that this monoidal functor can lift to the centers. Right? So what does it mean for this E now to lift to a functor from Yetter-Drinfel'D modules over A to Yetter-Drinfel'D modules over K? It's something you can write down. These Yetter-Drinfel'D modules are co-modules over some co-ring. You want to lift a functor between the base categories to categories of co-modules over a co-ring. What you need for that is some kind of an entwining map, but not the usual entwining map. It's what I call a YD entwining maps, because these are not just co-modules, but Yetter-Drinfel'D modules. So the co-multiplication, the actions are a bit more involved, but there is some kind of entwining map and with conditions.
Yeah, from VLB, I think it's important to know how you say it in French. And it's structure enlacée.
I knew it in Dutch before when I wrote my application for RWO. Since I'm at ULB,
So at your university, you were a problem.
ik verschil de structuur in Nederlands. Okay, so
Wait a minute.
Yes.
So in the first point, you are insisting that it is this functor is continuous. So it is in the spirit of the WAS.
yeah, let's just add like what's you.
But why?
I mean, because it's quite
To have this algebraic
yeah. I mean,
interpretation of this
you
functor?
can indeed do it with more general functors.
Yes.
But in the end, I want to go to these generalized Yetter-Drinfel'D modules, right? So I want these generalized Yetter-Drinfel'D modules, which are not just modules over A, but they have this additional co-action of a co-algebra C. So the point here of this is that this co-algebra comes up exactly when you want to construct a center of such a bi-actigory. The center of the bi-actigory needs this op-monoidal functor between the monoidal categories over the bi-algebras. And these op-monoidal functors give you exactly these co-algebras under the mild condition that this functor is co-continuous. So
So this is, in a sense, is a correspondence
yes,
between these two
yeah.
categories.
So if the E is strong monoidal, right, then what does it mean? It means that the C, the co-algebra, is not just a bi-co-module algebra, but it is a Galois object, a Galois co-object at the left, at the right over H. It becomes Galois exactly if E is strong monoid.
Strong monoidal.
And you can do more if you want that the right adjoint of C, so E is tensoring with C, so it has a right adjoint, which is a homing with C. The right adjoint being strong monoidal, this gives you that it is a Galois object over K, provided that C is finally generated in projective over K.
Sorry, give me a completely dummy question. What's the difference between object and co-object?
A Galois object is a co-module algebra that satisfies the Galois condition.
Yes.
A Galois co-object is a module co-algebra that satisfies the Galois condition.
So the theory is parallel to the theory of
Schauenberg
about
exactly this.
Galois objects.
Yes. I mean, this is just Schauenberg basically turned
The arrows reverse.
yeah. But
Yeah.
I will come, yeah, the reason why I like this approach better is I find it easier to work with co-objects than with objects because I can use the tensor product in terms of co-tensor product, and that's.
So that's a special case of these Galois co-extensions.
Yes.
Regimes.
Yes.
Yes, yes. Okay, so if you round up, the most important part here is in fact, so that the optimal structures give you the co-algebras, and the last thing is, if I want E to be a monoidal equivalence, that means exactly that C is a big-Galois co-object. Again, Schaumburg, this is for objects, right? So the Galois objects between two big-Galois objects are exactly monoidal equivalences between the co-module categories. Then. So here is between the module categories. And in fact, so again, why I like these Galois co-objects is because you can, I think you can write down the things quite well. So you have these, what means Galois object or Galois co-object means that you have a bi-comodular algebra and you have these canonical maps that appear. You want these canonical maps to be bijective in order to have a Galois object. So you have them for the left action of K, you have them for the right action of H. And if you have all four of them to be bijective, then it's a Galois, big-Galois object. Okay. What you can do then is you can make out of a big-Galois object a new one using the opposites or the co-opposite of the co-algebra and change the actions with the inverse of the antipodes of H. Right? So if I started with a KH bi-module co-algebra, then the opposite becomes an HK bi-module co-algebra using these inverses of the antipodes with the actions. And then when these canonical maps here are invertible, you see I can go from C tensor C, I can go to K tensor C, and then the copy of C I can kill with the co-unit. So you get maps going from C tensor C to H and from C tensor C to K. Well, these maps will give you exactly a strict Morita context when you have a big-Galois object. And this strict Morita context is what...
And are they like co-translation maps? Are they like...
Yes, they are exactly that. They are the equivalent of the co-translation maps. But here they give these translation maps, co-translation map gives you the Morita context. That is
By monoidal, could you come back to this gray frame? It's a monoidal equivalence. So are you assuming that it is strong monoidal?
Yes. So monoidal equivalence means strong level. Yeah.
Equivalence.
It's equivalent as monoidal categories. Okay, and then so these big-Galois objects form a groupoid, just as the Galois objects do. The inverse is exactly that C bar. Okay, you can, in fact, also, this is also from Schaumburg, you can, if you don't have invertible antipodes, you can still find the inverse, but it becomes a bit more complicated. It's not so important for us. What is more relevant is the following remark. So remember in these generalized Yetter-Drinfel'D modules, one of the variations of Panaite and Steich, we had these alpha and beta, two automorphisms of the Hopf algebra, and we had these deformed Hopf algebras. So these deformed, you deform the actions by alpha and beta, and you keep as co-multiplication the usual co-multiplication. Well, these objects are exactly big-Galois objects. And in fact, as big-Galois objects, you can just turn the beta, for example, to the right, and it's enough to have only one automorphism at the right. So this one and this one are isomorphic as big-Galois objects, and so they give the same equivalence of monoidal categories. So to sum up, you have a morphism, a group morphism from the group of automorphisms of H into the group of big-Galois objects. Or the groupoids, the group of big-Galois objects over a single H. Good. And so this is just Schaumburg reversed. Okay, then what is now, in fact, the main theorem that we have is that these generalized Yetter-Drinfel'D modules over Yetter-Drinfel'D datum, so we have two bi-algebras or two Hopf algebras a bi-comodule algebra, a bi-module co-algebra. These generalized Yetter-Drinfel'D modules, they are exactly the center of the A modules viewed as A category relative to the functor, the op-modal functor that is induced by the C. And how you prove this is basically the same as the classical thing that I recalled in the beginning. So if you have an object in the center, you need this half braid. But the half braid now goes from tensoring to M on the right to tensoring with M on the left. Then at the right here, you need to apply that functor E. The half braid was going from object tensor M to M tensor, the functor applied to the object. So there's this extra C coming.
Yeah, so even if this function is not co-continuous, you still have the name with E.
Yeah, indeed. Okay. Good.
I have a slight problem with this isomorphism because on the left-hand side, I have all four players, A, C, H, K.
Yes.
But on the right-hand side, K is missing.
No, K is inside the bi-category structure of this category. So this M is in fact an M in its
H has decorated.
yeah.
So with H and K.
So indeed, exactly. So A is an H K bi-comodule algebra,
So maybe up
and this C
indices.
yeah, this C, yeah, it should be better up, is in fact a functor going from H modules into K modules. So
Yes.
it's not written, but it is there.
Okay.
Right? So it's inside the structure. So again, if I have something in here, I have this half braid. And again, a half braid is a natural transformation between two functors on modal categories. It's enough to know it on the algebra. So it's enough to know beta of H. And beta of H gives you, just as in the classical case, a coaction on your A module, but a coaction now, a C coaction. This image of beta lands in M tensor C. And then just as before, if you express what it means beta, for this beta to be A linear, it gives you the Yetter-Drinfel'D condition. If you want beta to satisfy the half braid conditions, you get the coactions. And if you want beta to be an isomorphism, you need not conditional C, but you need A to be a Galois object. So A becomes also a Galois object if you want these braidings to be invertible. Yes. Okay, and now by applying this theory, if this functor tensoring with C, if we want to lift it to Yetter-Drinfel'D modules in order to have some kind of a braided category, then we need the C to have this YD entwining structure, or what is also good enough, of course, is of much stronger than this is to have that C is a big Galois object. Then this happens automatically. So this is then, yes. Okay, but we can go further, that was within there. So we can do a bit more than this. We do not just have, well, we already solved more or less the problem in the sense that now I know what is this braided structure on one single generalized Yetter-Drinfel'D category. You have a kind of braiding where I can braid with the classical Yetter-Drinfel'D modules from the left over H to the right over K. This is what we have, but we have something that is even a bit more general. So if I indeed assume that I have a big Galois co-object, so this D is, I should use the other one. Yeah, D is a big Galois co-object, and C is just a usual co-module algebra, but I have over the same Hopf algebra at the left and the right. So I have these Yetter-Drinfel'D modules where I have the Hopf algebra at 3 spots, the same Hopf algebra at 3 spots, but the co-algebra is a Galois co-object. Okay. Then, when I take a Galois co-object like this, I can go from this Yetter-Drinfel'D category to this one. So the H becomes a K, And the C, you tensor at the left with D and at the right with the inverse of D in the groupoid of Galois co-objects. Okay. Here, it's written how this functor works in terms of the half breaks. So it's the same as, again, this is a generalized center, this is a generalized center, and this tells you how you turn the half braid at the left into a half braid at the right. Not sure if it's useful to write what to go over all of it, but what is important to remark maybe is that I really use here that D is invertible in this groupoid of Galois co-objects. So just having the Hopf algebra K appearing here allows it to turn it into D. I use here that tensoring with D over H is a monoidal functor, a strong monoidal functor. Here we use the half braid that we had before to turn these things around. But if we do that, you need to plug in the C. That's how the half braid works in this category. And then again, you use the monoidal structure of the functor tensoring over D with H. So the main point is that it works. You have this kind of functor that allows you to go from one Yetter-Drinfel'D category to another one, where you have 3 times the same Hopf algebra. So again, these are loops in this B category, but it's a bit more than loops. Also, you have here at the left, this H is, the A is just H.
You cannot replace this H by some Galois object.
Not yet. So it's exactly my frustration. I wanted to do this for a general A, but I will do this. Like, so far we only have this. Well, this is the same thing. These B Galois objects give you these kind of functors between these categories. And then we have this kind of braided structure on these generalized Yetter-Drinfel'D modules. So I have an arbitrary kind of Yetter-Drinfel'D modules here. A general one that you can have with 4 different objects. But on the left, I have specific ones. First of all, they are loops, but moreover, the A is an H. I can tensor these together and then I land here. So since I had the algebra here was trivial, when I tensor it with B, it's tensoring over H, so the B is not changed. When I tensor these two, I need to go to D tensor H. So the co-algebra changes. And the algebra here is the same. Then, if I switch them, I use the identity on the generalized, on the usual, on this category of generalized Yetter-Drinfel'D modules. But on the left-hand side, so remember the idea is that you are working in a P category. So here you have like true arrows, whereas here you have a loop. Okay. I want to turn them around. I still have the same arrow. But then here now, I need a loop, but a loop on a different point. Right? So this was moving from H to K. This is going from H to K. So here I need something that is going from K to K. And for that, we need that functor that I had on the previous slides. That allows you to turn this category of generalized Yetter-Drinfel'D modules with 3 H's into another category of Yetter-Drinfel'D modules with 3 K's. And then our gradings look like this. You have an M tensor N. When I move the M to the other side, there is a D tensor H that is showing up. So it's very Yetter-Drinfel'D-like. If you want to turn around 2 objects, you have to kick with one on the other. Okay. So these are the kind of braidings we have. And now, if I still have some time,
yeah, I have 12 minutes.
Okay, I want to say something about how you can interpret the structure that we have as some kind of cross-braided B category. So there is this notion introduced by Thurijf of a cross-braided monoidal category, a G cross-braided monoidal category where G is a group. What is the kind of structure you have? You have a category which is graded over the group, meaning that your objects are in one of the homogeneous forms Or you can, again, as on previous slides, instead of having this disjoint union, you can write kind of a co-product so that you have objects that are sums of homogeneous degrees. Co-products of homogeneous degrees, okay? And you want this grading to be compatible with your monoidal structure in the following sense that when you tensor two homogeneous objects, you have length in a homogeneous object of the product of degrees. Yes. But the group is not just getting a grading on the category, but at the same time, the elements of the group give you monoidal automorphisms of your category.
Sorry, so this time it's a usual disjoint union. It's not a product in the categories.
You can take it as this kind of co-product. So here in the definition of Turayev, I believe he writes the disjoint union, but there is a remark that like when you want to do it in an abelian setting, you have to take something more general, or like allowing direct sums basically of objects of this kind. Okay, so the group grades the category, but at the same time, it acts as monoidal automorphisms of the category. So for each element in the group, I have a functor, a monoidal functor from C to C, but which changes the degrees in this way. So if I act with an element of the group on an element of degree G, I go to an element of degree H minus 1 GH. So there is this adjoint action on the degree. And then you have gradients like this, and they indeed very much look like what we have. You have beta xy. When you twist them, you have to kick with one on the other. So there is this, the y is of degree h, and the degree h is an element of the group. It can act on this x. And you see that here I had something of degree h, degree g, degree h. So the product is gh. This is degree g. And this one, no, this is degree h. And this one is h minus 1 gh. So
It cancels.
so it cancels. Yeah. The h and the h minus 1 cancel it. Fits. Okay, so this structure is indeed something that appears in generalized Yetter-Drinfel'D modules. That's again Panaite and Steich. They have the group they consider is the product of the Hopf-algebra automorphisms with itself. So they have these alphas and betas, and the alpha and betas give you the grading and the twist, and well, everything fits with the definition of this derived category. When we want to do this, we don't have just a monoidal category, we have a B category. So our aim is to do this. Yeah, so this is what we had. We want to do it.
So now you have two groups. Automorphisms of
No, it's the same. The group is the
Okay.
product of the two.
okay.
So they have just two copies of the same group because they have the alpha and beta. But somehow, like I said before, this alpha and beta gives you different alpha and beta give you the same functor basically. Yeah, so you can put identity and alpha to the other side.
So the previous small h now is a pair alpha beta.
Yeah, indeed. Now we want this in the B categorical setting, and what you can do is you can define a groupoid cross-braided B category. So we do it the same as before, but we do the B categorical version instead of monoidal category. So we have the group becomes a groupoid, the monoidal category becomes a B category, and the B category should be graded over the groupoid. What does it mean? The zero cells of your monoidal category are graded by the objects of the groupoid. And whenever I have the home category between two objects, so I have an A and a B, two zero cells. I have the BAB is a home category in the B category. This should be graded by the sets of all arrows in the groupoid going from the degree of A to the degree of B. This way. And then you need that horizontal composition. So that's in B categories, the monoidal structure becomes horizontal composition of one cells if you want. This should be compatible with the composition in the groupoids. And you need that the elements of your groupoid give you functors like this. So again, this is going from loops to loops, right? I have an object A, I have one cells from A to A, I can turn them into one cells going from a B to a B using an element in the groupoid that is going from degree A to degree B. And then when you do this, you can say what is something braided. And again, this is like we had before. XY, you go to YX, but kicked on with the degree of Y.
So I have a question about this notation. So this partial comes from
this partial is the grading, is the grading. So elements, zero cells have a certain degree, and partial tells me what is the degree of the zero cell. So every zero cell in my category has a degree. Okay.
But I'm asking about the origin of this notation partial. Does it come from the cross-module theory?
Yes.
Yeah. For the fundamental group. And...
Yeah. There are examples that come from cross modules of these derived categories. Okay, but unfortunately, this is not exactly what we have. And the reason is, like you mentioned, like I said before, I had this problem that on one leg, I needed the H instead of a general A. So what we actually have so far is something a bit more ugly. We have a double groupoid cross-braided category. So what is different on this slide as before is that now I have two groupoids that appear, G and H. Right? I have things that are braided both over G and H. So there is a double degree. There is a degree in G and there is a degree in H. And here you see this is very Yetter-Drinfel'D, generalized Yetter-Drinfel'D type, where I had Yetter-Drinfel'D modules with the zero cells being my Hopf algebras. And then the 2 degrees is on one hand the algebra and the co-algebra. Okay. And in my setting, the two groups will be the groupoids, the two groupoids will be the groupoid of Galois objects and Galois co-objects. And then, so I have these morphisms, and here you see the thing that's annoying me a little bit is I want these groupoids to act on my B category, but fixing on one of the, so the G acts on objects where I only have the units, the degree, the trivial degree, in the other groupoids. So I have the two groupoids G and G prime. Elements of G act on my category, but only in the trivial degree for the other group. And the elements of H act on my category, but only in trivial degree on the groupoid G. And then having gradings. And having such a structure, that's something what I have on these generalized Yetter-Drinfel'D modules. So again, the gradings are over Galois objects and Galois co-objects. I can do the grading. This is the same as what I had before, but the grading goes, the braiding uses this functor that goes from this one to this thing, where I have here not a general A, but only an H and a K that appear. So what I would really like is to be able to replace this H and K by general A's and B's and have something like this. That would be nice. The problem is that so far we were not able to cook up a functor of this kind, such an omega, using only the data that is written here. So basically I need to use this B and D to make a functor like that. And that I was not able to do. I can only do it like on the previous slide. Having just an H here, I can use this D to make a functor like that. I'm not using the B yet. So somehow I want to use the B, but the only way that I can use the B is by taking this C to be trivial, and then I can do it. So I can somehow separately make something like this, taking C trivial, then it works, taking A trivial, then it works, but taking both of them non-trivial, and for the moment, I don't see how to do it. I know how these functors should look like, because they are functors between module categories. They should be induced by tensoring with a bi-module, bi-co-module, thing like that. But I was not able to build some omega using only data coming from here. So, yeah, that's the remaining.
Is this problem that you need a functor which is on one hand, it must be monoidal and monoidal. So in a strong case, it would be.
No, the strong case is not enough because I'm already working in the strong case here.
Okay.
Because I suppose here that this D is already a Galois co-object. So my functor on the category of H modules, from H modules to K modules, is already strong monoidal.
Yes.
It's a strong monoidal equivalence. It cannot become
Yes,
anything better than this. The problem is.
And this is not enough.
No, because you can see what is my problem. If I this slide, so our problem is if I want to use D is a bi-module, but over H and K. So what I can do is, like I did before, tensoring over H. But here I don't have H modules, I have A modules. So I cannot tensor these things together. The same, if I use the B here, I can use a cotensor product. But again, a cotensor product over H with B, that I can do, but I don't have a coaction over H, I have a coaction over C. So I think, again, still think it should be possible because when A and C are also B-Galois objects, A is not that different from C and so somehow, not that different from H.
But there are twisted versions.
Yeah.
So maybe
So-
some auxiliary twists are needed.
Yeah. But yeah, just to say that it's not completely the end, but it's the end of the talk.
Okay, thank you so much. You prolonged your talk only by 50 seconds.
Okay.
Okay, let's begin with further questions. Anybody from?
I have a question. Fine. So all your generalization goes through the following way. We focus on the categories of modules and cook up some centers. Okay. What about focus on co-modules
Yeah. So it's
and using Schoenberg theory?
yeah, that works. So this basically is what I'm doing here. So you can indeed do the very same thing as what we have here, only instead of having a C, I put an A, right? So then my co-tensoring with the A will be using Schoenberg monoidal equivalence between the co-modules over the Hopf algebra, and that's how it works. So that's, I didn't write it on slides, but it's basically hidden in the fact that I say that, where am I going here? That we have this kind of double group weight cross algebra structure. I basically only set what are the Galois co-objects, how they act, but the Galois objects will indeed act in the same way, and you have both. Inside these generalized Yetter-Drinfel'D modules, you have, so far we have two types of braidings. The one that I really explained you with the Galois co-objects, that allows for the twist, but indeed using the Galois objects with the twist, you also have this kind of braidings, right? So then you have the red part here, right? So if the red, the black part would be trivial, if C is just H, and you put H in here, you see you have D tensor over H, if just D, and then D tensor D bar becomes K. Then all of this just becomes K, right? And so these generalized Yetter-Drinfel'D modules, again, I can use the action and the co-action. I can, with both, I can do the twist and have these braidings. Unfortunately, I cannot combine them into the most general twist that I would like to have.
Okay, so
But the dual theory is there. Yeah.
yes, I understand this. But if you could come back to the main theorem. Can you apply Schoenberg's results to obtain something like this?
Yes. Indeed, so I didn't write it, but it is
to the center, but now
the center of
another functor, it would be probably some.
modules over C, where your functor will be cotensor products
Cotensor.
Yeah.
Oh, yes.
with like this. So you have that as well. Yes. But I didn't write, but we have.
Yeah.
We have both.
Okay. Nice.
So this blob is a tensor product.
Yeah, that is the cotensor product.
Cotensor. Square.
Mhm.
Okay, so this suggests that there could be some path using both approaches. Because you have some center of one monoidal category, a center of some other monoidal category. One is based on modules, another one is based on comodules.
Yeah.
But at some moment, you see that it is not enough to keep only one point of view because of these twists.
Yeah.
Okay.
Yes.
So maybe there could be some way using some kind of center with respect to both structures, algebras and coalgebras together.
Yes. Could be.
Mhm. Maybe it's my stupid impression, but
Yeah, I mean, it's getting.
because Yetter-Drinfel'D are defined as usual Yetter-Drinfel'D, if everywhere you have H. Okay, this is the center of some category. Okay, but you see that this category is not unique.
No.
It could be center in one category, it could be center in another category.
Yeah, so I mean, it is like the center of H modules, but also the center of H.
Yes,
So
yes.
you have that same picture there.
Yeah. So this ambient category in which you are considering this center, this is not unique.
No.
So maybe besides these two paths, one preferring modules, one preferring comodules, maybe there's a path using both.
But yeah, you're switching the role because you are the modules and the co-module, so A and C, but one is for the category, the other one is for that functor. So if you want to use both of them in the functor side and what you put in the module side or in the category side or the other way around, I don't know. I'm not sure if it's possible to. Or yeah.
So maybe in this strong monoidal case, maybe it would be some way of because from one point of view, you are using one structure and another half of the structure is used for some twists.
Mm-hmm.
In this dual picture, you are preferring this
Yes. So in
whole structure, and this structure is used for constructing twists.
It's giving you one type of twist,
Yeah.
and the other one is giving you the other type of twist. And then
Yes.
so you need to combine. And it's indeed exactly like somewhere hidden in this construction as a center. It is hidden that I work all the time with, if I go back to this slide here. So my problem here that I had, like I said, was that I would like to have this H to be just a general A. But in the way we construct these Yetter-Drinfel'D modules as a center, we did it as a center with respect to H modules and K modules, if you remember this. So if I go back here, basically, yes, I think I had it because you asked it, where is K and H? Yes. So this is a center with respect to a functor that is going from H modules to K modules. If I would like to do it more general and have this, at this moment when I do the twist, replace the H with an A, I have the feeling that already at this point, I should put an A here and let's say a B here, and have this C to be some, not a bi-comodule algebra, but a bi-module over bi-comodule algebras with some more additional structures. So at some point we started to look into this, but I'm afraid that when I do that, that I will find Yetter-Drinfel'D categories that are even more general than the ones that we have here. And I think somehow to solve my problem, that there is probably a setting where it works, but then you will have even more wild Yetter-Drinfel'D modules than the ones we have.
Yeah, so I ask you because I remember our paper with VERCRUYSSE that if you are interested only in Galois objects, so this works perfectly well. But if you want to think about homogeneous spaces, not
Yes.
not
Yeah. I see. I think that is also something I want to figure out once. Indeed, when you, instead of Galois objects, you take Galois extensions, how does it relate to this kind of stuff? But yeah, that's, I don't know for the moment, but it's indeed something natural to ask. And
Yeah, then instead of bialgebras, we need to take bialgebroids.
probably
probably
yeah.
because in Scheinberg theory,
Yeah.
passing to this
Of course.
groupoids is natural. And also in your examples, you pass to this groupoids.
Yeah. And the question you asked at the beginning, in fact, what is this structure of the double that you, where is it here? I don't know. But it's somehow hidden in this big category structure on the Yetter-Drinfel'D, right? So it's all the way back. I don't know where is the slide, but yes, here. So if you know that your generalized Yetter-Drinfel'D modules are a B category over these things, and you go everywhere to the doubles, if everything is finite dimensional, then you see indeed that the double of this thing becomes a bi-comodule algebra over these things. And indeed, if everything is Galois objects, and this double will also be a Galois object over these doubles here, like you said in the beginning. That should still be true, I believe. That
So this is like in derives.
yeah.
Not in derives, like in Scheinberg's by Galois objects.
Yes.
You have to this.
It will again be that because these.
Mike, are you done?
I know. Thank you.
Anybody else from the net, perhaps? Adam,
No, I don't have any question. Thank you.
any comments? No.
Very nice talk.
Okay, that's a good comment. So to wind up, allow me to ask you two questions. One is a very general philosophical one. Of course, I love the idea that you have something which is generalized by brute force, because you can. You have this very broad concept of what is a Yetter-Drinfel'D structure, which encompasses all sort of Yetter-Drinfel'D modules, alpha, beta, generalizations, whatever. It's all in there, which is nice. But then, okay, it's kind of done by hand. And I understand that you conceptualize it, say, hey, what was the typical feature of a Yetter-Drinfel'D module is that it gives you center of some nice category. Well, it works as well. You just have to unravel what the categories. I understand the beauty of that theory. However, on a more practical note, what is it good for? So if I know that I have a center of a category, what does it allow me to do? So for instance, when we prove that a given sister algebra is a graph sister algebra, then we can read over K-theory, we can see the generators, we can do lots of things, quantum CW complex structure. And we have so many more tools once we prove that, hey, this is a graph sister algebra. So now that you prove that this is the center of some category, what tools does it give you? What can you do what you wouldn't be able to do otherwise?
One of the things is, so I mentioned this work of Logwitz and Walton, who did something similar, like this, or what did they call it? They also have a center, a reflexive center, they call it. And what they then indeed show is that if you want the double over it, also has some kind of quasi-triangular structure. And this indeed gives you more tools to work. And it's something we did not do yet, but I believe there should be on these generalized Yetter-Drinfel'D models. If you go to the double, there will be some notion of R matrix that you can build on these things, and that's hopefully indeed can give you some extra tools to work with these categories. But that's something, yeah, for the future or for now.
Theorem.
Yeah. So once you have indeed the center and the braiding, then you can look what is the R matrix in that setting and go from it.
Yeah, I mean, one should not forget that one of the big applications of having Drinfel'D doubles to have this quasi-triangular structure in knot theory. So this is reminds me of Kaufman and Radford. Okay, another technical question. Structure enlacées are very dear to my heart. So would you be willing to elaborate a little bit on what kind of YD entwining structures you get, and in what sense our canonical entwining structure that we have with Brzezinski are special cases?
Well, it's something we did not completely work out yet, but what I can say something about it, maybe, here it is. If I, no, it was further on this YD, I guess. No, where did I? To think structure of my dog. It's lifting to. No, it must be much. So it comes from lifting a functor to a functor of your generalized Yetter-Drinfel'D modules. And I mean, that's something well known, how this relates to these kind of entwining maps, even for monads and so on. Right? So what we basically have is YD H, let's say, okay, with a forgetful functor to modules over H. And when we have a co-algebra, a bi-module co-algebra, this gives us a functor to modules K. And here we have a Yetter-Drinfel'D's modules over K. Okay. And what I want is to lift this functor to the Yetter-Drinfel'D modules. Okay. Now, this is co-modules over some co-algebra of the form, or some co-ring of the form H tensor H with non-trivial actions and thing. And here, this is also co-modules over some algebra, some co-ring K tensor K. The annoying thing is that when you go here, these scoring structures are non-trivial, so they really use this Yetter-Drinfel'D actions and structure. But you can, in principle, apply the general theory of lifting a functor between base categories to functor between Allen-More categories over some comonads and so on. And then just means that you need that this functor has a twist with the free functors that you have. So from here to there, you have the free functor, which is tensoring with the coring over the base. But you see, you will tensor H over H with something. So one of the copies of H will disappear. So basically this functor is a tensoring with H. And the same one, this is a tensoring with K. Up to some non-trivial isomorphism.
No.
And you need that when I tensor with H, I just tensor with H, and then I do my functor. It should be the same as first doing my functor and then tensoring. But basically what you get out of this is a map like this. Only to find out the exact compatibility conditions. I said you can define it, but we didn't write down exactly what are the things, because you need to go through this equivalence from Yetter-Drinfel'D modules to modules over the scoring, see what are the compatibilities in the general case, and write them down explicitly here. We didn't do this yet, but I'm not completely sure because I didn't prove it yet, but I'm almost sure that one way to get these is to use the Big-Galois objects. So the Big-Galois structure should give this, or is here, right? So to have this kind of map from key, what was it? Just go back one slice, from H tensor C to C tensor K. If I want to go from H tensor C to C tensor K, it cannot be right like this. It should be the other way around. Should have looked here. C tensor H to K tensor C. Okay. When I apply here the inverse of my canonical map like that, I go into C tensor C. And then here I do the inverse of the canonical map. I have a candidate of my YD entwine. And I think this is the one that should come out of it.
So that should be our canonical entwining, right?
Yes, yes.
Yeah.
Okay. But again, I didn't do the calculation, so it's a guess because, well, needing a map of that kind and having something very natural coming out of it, I expect that one should be the one that's.
But you know what confuses me is that when we speak about entwining and when you have these
you have the same.
exactly, yes.
And here it's because it's what you do when you do an entwining structure, it's also this kind of lifting thing. Right? You say but there you do it so when you entwine, you have you want to lift so we have modules over K down, and you have, let's say, modules over A here, and you have a co-algebra which gives you a co-monad functor on the category of K modules, and you want to lift it to a co-monad on A modules. That's how you get your entwining in the same way as here. Because you say, this functor, I need to lift it to A modules, meaning that it should commute with a free functor. But you have 2 times the same A appearing here. That's how you get the usual entwinings. Here, it's entwining, but entwining between 2 different categories. So, and that's why they are different. So it's more, I mean, again, in a more B-categorical level, these entwining maps, they also appear in the formal theory of monads of street, as you have these kind of 2 cells which are exactly this kind of entwining, but between different things. And then on, again, the loops in this phi category, they are the entwinings from unit, okay, in some cases.
So the point is that entwinings or some other kinds of twists, they are more general than this one coming from this canonical map. But the point is that in this canonical map situation, the point is that if you assume that you have any entwining, you know that this entwining is unique.
Yeah, yeah, indeed. That is again indeed this this structure. Like when you say here, there is a bijective correspondence between liftings of the functors and some entwining maps satisfying some structure. So here, this is additional structure you have. Whereas if you have the small monoidal equivalence, there is only one possible choice.
Yes.
It's already there.
Yes.
So it's indeed, but that's the difference between here you can have more structure because you only assume that the functor is up monoidal and not really strong monoidal. Whereas when this is not just up monoidal, but really strong monoidal, then it forces this thing to be a property instead of a structure. It's determined.
Exactly. Yeah, I'm very happy with this. Thank you. However, this was still too categorical for my taste. I would love to see, like in mixed distributive laws, entwining, we have some clear-cut algebraic axioms. So I'd like to see some explicit conditions for such an entwining between 2 different categories. But I think we can do it at dinner.
Yeah, I mean, it's like I said, we still need to do the calculations, but we know it exists.
Okay. So I think it's a good point to wind it up and stop recording. Let's thank JOOST again.